Hello everyone, I'm Professor Muthana Ahmed, and in today's class we're going to continue on with chapter 3. Before we do that, we'll just do a quick review on what we've done in the previous class. In the previous class we compared heat transfer to Ohm's law, which states that current equals the change in voltage divided by the resistance. Meaning that for a current to travel through a wire, there needs to be a change in voltage, which is the driving force. Okay, and some of that current is lost due to resistance. Similarly with heat transfer, which equals the change in temperature divided by a thermal resistance. The thermal resistance depends on the type of heat transfer. For example, in conduction, the resistance equals L over, let me rewrite this. The conduction resistance equals L over Ka, whereas in convection, the resistance of convection equals 1 over HA. Going back to conduction, the heat transfer equation itself, which is Q equals dT over change in temperature divided by R conduction, this equation itself is only true if it meets 4 specifications. 1, it's a one-dimensional. 2, steady state. 3, no energy being generated in the system. And 4, constant K, meaning that the thermal conductivity is not a function of temperature. Unless these 4 requirements are met, this equation here can't be true. It's only true if these 4 requirements are met. Okay? Whereas in convection, this equation is true in all circumstances. Okay? Now, we also covered in the previous class the thermal circuit. We've developed an understanding of how to draw it, which is basically simple. It's that, hey, heat transfers from the higher temperature to the lower temperature, and as heat is traveling, some of that heat is lost to resistance. So that is your conduction resistance. This is your T2. T1 is higher than T2, which causes the heat to transfer from T1 to T2. That is similar also to in convection. Same diagram. T1, T2, heat is transferring from T1 to T2, and some of that heat is lost to convection. Now we can start with an example of a composite wall with 2 different types of material. This here is our wall. Actually, let's just make it a rectangle. And here is our wall. Wall has 2 types of materials in series. This is material A and that's material B. Each wall has its own K value, thermal conductivity. Okay. Heat is transferring from the left side to the right side. On both sides of the wall there is convection. Therefore, there's a temperature of the surrounding, T infinity 1, T infinity 2. There's also a convection coefficient on both sides since there's convection. This here is the surface temperature of A, material A. surface temperature of A slash B, and this is the surface temperature of material B. For the areas of the wall, we'll assume that TA equals TB, therefore we'll just call it area. The length of the materials is different. This is LA and that is LB. Now the objective is to find Q, total Q. Now before we start solving that example, the first step we need to do is convert this schematic here into a thermal circuit. So the thermal circuit, you need to write down the first point, the first temperature, which is T infinity 1. That temperature, as heat is transferring, it goes through a resistance. The resistance is convection resistance 1 due to the convections that's taking place in this area here. Some of that heat is lost to the resistance before it reaches surface temperature A. Same process again. Heat is transferred from this point. Some of it is lost to our conduction A before it reaches TA slash B. Same process. Some of the heat is lost. R conduction B before it reaches TB. And again, some of the heat is lost to convection 2 before it reaches T infinity 2, our final point. Now, to start solving, we know that Q, heat transfer, equals change in temperature divided by the resistance. Now, the changing temperature we want is for the entire system. Therefore, we're going to be using T infinity 1 and T infinity 2 for the change in temperature. For the resistance, we'll use the resistance in between, the total resistance in between, which is the summation of all the resistance in the middle. Therefore, Q equals T infinity 1 minus T infinity 2 divided by all the resistance in the middle, which is R convection 1 plus R convection 2 plus R conduction A plus R conduction B. Okay? And that's how you get the total heat transfer. For example, if you're also asked to find TB, temperature TB, which is usually not an easy temperature to find, what you need to do is make a cut point in your thermal circuit and solve it the same way you solved for total heat transfer Q, which is Q equals, which can be written as T infinity 1 minus, that's your cutting point, TAB divided by the total of resistance in between, which is R convection 1 and R conduction A. R convection 1 plus R conduction A. That is already given. You solved for it in the previous step. The only unknown here is TAB. Okay? Again, for example, if you're asked to find TA, which is an unknown, you can say that Q equals T infinity 1 minus TA, that is the cutting point here, And the resistance is the resistance in the middle, which is R convection 1, and so on. Now, in order to find these resistance here, you'll basically say that, I should have went through this earlier, our convection 1 equals to 1 over H1 times A. Our convection 2 equals 1 over H2 times A. Our conduction A equals LA over KA times the area. And our conduction B equals LB divided by KB times A. And that's the values for each one of your resistances. And that's it for this class, which basically shows you how to solve a composite wall in series, how to find the heat transfer of a composite wall in series. In the next class, we'll go through an example where you can find the heat transfer in a composite wall in parallel. See you in the next class.